Hello, myself Aditya with my teammates Vaibhav and Aparna are presenting our analysis and model on predicting readmission rates for patients having diabetes in Caucasian race. So, according to a study conducted in October 2010, diabetes requires the most healthcare use. This was one of the many findings by the group of analysts who believe hospital leverages such type of models to focus on certain patient groups and also emphasize the influential clinic risk factors for better health. Our experiment on the data intends to build a model to study the various clinical risk factors of an individual patient and find their implications in predicting if a patient would be readmitted to the hospital or not. Our project also opens up opportunities for researchers to study the discovered risk factors and leverage it for a better preventive care. So, so during our presentation, we'll be talking about objectives, data preparation, descriptive analysis of data, model building, and finally we'll be discussing about our findings and our final result. So coming on to our objectives, diabetes is a leading cause to many other diseases in patients and requires proper attention and changes in medication accordingly at an early stage. The main objective of our project is to provide actionable data for the use of hospitals, clinics, which will be primarily focus of this project, charge which will provide a change in medication and take preventive measures for other diseases associated with the readmission due to higher levels of diabetes. We also aim to identify the risk factors involved in patients' readmission to the hospital suffering with diabetes and associated factors leading it to by study patients' previous clinical records when he was last hospitalized. Coming to the data preparation, so our data was accessed from UCI repository for machine learning. Our data was an extract representing 10 years of clinical care at 130 hospitals and delivery networks. Our data was in .data format, which was then converted to .csv format for better understanding. Data cleaning deals with the identification of the missing values and outliers which might distort the data and provide inaccurate analysis. The data obtained was in crude form and had many error values. The data had to be checked for missing values. The columns like pairs code and weight had 54 and 97% missing values respectively. Hence, these columns were removed from the dataset. There are also some duplicate rows which we removed them. So coming on to the data transformation, our target variable readmitted had three levels and was a nominal value. Readmitted contained the values of patient being readmitted 30 days before or 30 days after. These values were replaced by yes or no. Also for the variable like age, we received the data in age ranges. We hence converted these values in ordinal values for the ease of exploration and modeling. So coming on to the data reduction technique were applied on the dataset to check if the number of attributes can be reduced. Principal component analysis was run on the specific set of variables to check if they can be grouped and determine a single variable which could represent the group. By having the look of the graph, we can easily say that the number of components will be 2. We now did a factor analysis with number of factors as 2 and the results are shown in the picture. Factor analysis and PSA helped us to confirm that we are not using any kind of variable that represent the same group. Now I would like my friend Vaibhav to continue with the descriptive statistics.
Thank you, Aditya. So as you just explained, we tried to use factor analysis and PCA to remove or reduce the number of variables which belong to the same group. However, we were not able to find any of them which loaded clearly on any of the factors, and hence we decided not to remove any of the variables. Also, we created dummy variables for our categorical variables so that we could use them for better data exploration and also the modeling process. Now, as they say, you should not start with the modeling process unless you understand the data better and how it's spread, basically its shape. So we decided to use the describe function in R and also looked at the basic descriptive statistics of each of the variable. We were able to find a few variables had high skewness and kurtosis values, while a few categorical variables were dominated by a single level. The variables with high skewness and kurtosis were number outpatient, number emergency, and number inpatient. These variables also had a lot of outliers. There are also two more variables named num medications and lab procedures, which also had a lot of outliers. Now came the part of cleaning the data. So our first approach of reducing the skewness of the three variables was to use logarithmic transformation. However, as you can see from the graphs in the presentation, that it did not help a lot in reducing the skewness, and hence we had to find a better approach or a different approach. Second approach for treating the skewed variables was to bin the variables in such a way that no single level dominates the variables. We hence tried counting the unique values in order to get sense of how the binning should be done. However, number outpatient and number emergency was dominated by the value 0 and did not have a considerable proportion of zeros and other values to qualify for binning. We have also included the snapshots for the proportions in our detailed report. However, number inpatient was the only one which led us to 1.972, which was the proportion of number of zeros and ones, and we hence decided to bin it and use it as a categorical variable in our modeling process further. Now was the time to deal with the outliers. Now, since we had removed the two variables with high skewness, we didn't have to worry about the outliers for these variables. And since also the num inpatient was being treated as the categorical variables, the outliers for that particular variable were also taken care of. So we were left with num medications and num lab procedures. We had to treat them for outliers so that we could use them effectively in our modeling process. So as you can see, we tried to filter out the values above a particular threshold, which eventually led us to a normally distributed uh, variable. At the same time, it also did not have any of the outliers. Now, we also had to analyze the categorical variables, and we hence decided to see the percentage of dummy variables against all the cumulative levels. As you can see, A1C result none, max glue serum none, race Caucasian are the levels which are dominating the entire column in the data. Had we used these columns in the data or not changed the data, these columns would have eventually turned out to be very important and would have biased the model. And this is not what something you would want to do. And this is the magic of descriptive statistics and analytics, because it helps you clean your data and it leads you in the proper direction for modeling. We hence decided to reduce our scope and filtered the data for A1 result none, max blue serum none, and the Caucasian race. This not only reduced our scope but also ensured that our model is not going to be biased. So now that the data was ready, clean, and we had understood all the columns, it was time that we could go ahead with the model selection. And yes, as the CRISP DIM methodology says, that we had spent more than 80% of time in data cleaning and understanding, and hence we could begin with the modeling process only in the last month of the project. So to give you an overview of how we are going to model, we are trying to predict the readmission rate or basically the probability of an individual to be readmitted based on various parameters of his medical history. So basically a dependent variable is binary, essentially if he would be readmitted yes or no. So the modeling techniques that came to our mind were the decision tree, logistic regression, and neural network. However, we didn't go ahead with the neural networks because it is kind of termed a black box model. It is difficult to explain, and at the same time, it is not only difficult to explain, but it is also difficult to interpret even for the analysts. So let me tell you a bit about logistic regression. Like linear regression, logistic regression is kind of flexible to non-linearities, and basically it doesn't require the assumptions which are made by the linear regression. Also, logistic regression assumes that the probability of event occurring, it is necessary that a dependent variable is coded accordingly. Dependent decision trees, the dependent variables are binary, hence regression trees is we have not used regression trees. No major assumptions other than the need to have a binary target variables are required by the classification trees. Logistic regression basically gives you the uh, estimates of your target variable, and it basically leaves you with a particular or a specific equation where you can punch in the values from your medical history, and it's eventually going to leave you with the probability estimates, and you could use a cutoff value and you can test different cutoff values and see where your model has highest accuracies. It hence becomes easier to explain to naive audience, and at the same time you can use the equation rendered by the logistic regression to basically programmatically develop a calculator where you can just punch the values and it would give up the probability or basically the estimation if that particular individual will be readmitted or not. So it can have various practical implementations in the medical and the insurance industry. Talking about the classification trees, it tries to make the data purer by using the homogeneity of data. It can either use the Gini index or the entropy. It tries to select the top variables in classifying cases, whether they would be readmitted. My partner, Aparna, would be proceeding with rest of the presentation, and she would take you through the modeling process and how we assess.
Before we began with the modeling process, we split our data into two parts. We created two separate training and validation datasets with no reoccurrences of cases in either of the sets. We created a 70-30 criteria because we had enough data, and this proved to be a fairly equal division of the data. To ensure that both the training and the validation datasets have similar distributions, we ran a t-test. From the results of the t-test, it was evident that the alternative hypothesis, that is, the true difference in the means is less than 0, confirming that our null hypothesis of means of training and validation data are same is true and cannot be. We have also run the describe function on the training and the validation datasets to ensure that there are equal distribution of the data in both the datasets. This was done for the continuous variables. Well, for the categorical variable, we have created a separate dataset and run again the describe function to ensure equal splitting of the levels of every categorical variable in both the datasets. This can be checked in our next slide. Moving on with our split dataset, now we consider our training dataset to build the models. The results from the logistic regression model are shown. The highlighted variables are the most significant variables which are important in predicting the target. The variables: number of lab procedures, number of diagnoses done on a patient, if there is a change in a medication or not, and the age group under 70, and the number of inpatient visits greater than 1 are the most significant predictors for our. A negative value for the estimate tells us that the variable has a negative impact on our target variable, and a positive value signifies a positive impact. For example, this means that a unit change, that is one value increase in the number of procedures other than the lab test performed, will lower the odds of a patient being readmitted by the value. Similarly, for the age group, we can say that for age group 70 or greater, the odds of a patient getting readmitted are about 0.03. Also, when there is an increase in the number of inpatient visits, the odds of a patient getting readmitted will increase by 8. Moving on with the other model, that is the decision tree model, we have built two decision trees based on a different. The first split criteria that we have used is the Gini index, and the other split criteria that we have used for building our decision tree is the least deviance or the minimum deviance model. In our Gini index, the decision tree gave us the most important variables to be number of diagnoses, the number of diabetic medications being none, and the number of medications being less than. From the results of our decision tree, we can say that if the value of the diagnosis of a disease is more than 6.5, and if the patient didn't take the medicine also, if the medication is more than 10.5, then it would be sure that he would get readmitted. If the diagnosis of the disease is more than 6.5 and no clinical procedure is done on the patient would be readmitted. Also, if the diagnosis of the disease is more than 6.5 and the patient is not taking any medication, the patient is getting readmitted. This is the easiness of understanding a decision tree. Well, this also makes sense in a practical point of view. The number of diagnoses when the number of diseases the patient is diagnosed with is less and the number of procedures or the complications taken care of is more, then the patient is identified as not getting readmitted. Also, when the number of diagnoses is less than 6 or comparatively less, and if the patient is administered medication for diabetes, then the chances that the patient does not get readmitted. However, the accuracy levels of both the trees are low, resulting in higher misclassification rate and hence don't look like good models and signals that there could be other factors which might provide better insights to the data. Moving on, we'll now assess the built models. Explanation of the chosen assessment and our choice to employ it will be discussed in this. We check the quality of the model by running the same models on the validation dataset. Accuracy of 70% with cutoff of 0.5 on decision tree gave us an accuracy of 50%. This was employed by using the predict function in R. Since we need our results to also make sense practically, let us also think in terms of the domain or business perspective. So according to our decision tree, a person who has been diagnosed with several diseases, that is more than 6, and who also skips the medication is obviously prone to be admitted again. This exemplifies the negligence that will adversely affect the individual's health. However, an individual who is diligent enough to take all the medications would not be readmitted, thus also confirming the potency of the medicines. Similarly, for our logistic regression, we can see that the females have a higher risk of readmission compared to men. This can also be confirmed from a report published by well, it's now time to decide on a final model and give a justification on why we chose the model. The accuracy of the logistic regression was better than the classification tree. This logistic regression model was chosen. This was not the only reason why we chose the logistic regression. The logistic regression had more variables included than the decision tree, which had a better explanation of the variances. Although the explanation of the logistic model is a little intricate than the decision tree, but it makes more practical sense with the real world and gives enough evidences to choose it over the decision tree. For example, variables like age increases the odds of a patient being readmitted, which also makes sense in the medical domain. Also, if the number of patients is equal 1, which means more visits to the patient impacts the readmission estimate positively. This makes sense as the individual might be experiencing multiple health issues, thus increasing the chances of his readmission. From our study of the data, we have determined the following variables to be important in predicting the readmission of a patient. The number of lab procedures being done, the number of procedures other than the test that has been undertaken, the number of diagnoses the patient is diagnosed with, and if there is a change in the medication that is being administered, if the patient is being administered proper diabetic medicine, and if the age group that being 70, and if the patient has more than one inpatient visit. Finally, I would like to conclude by thanking Dr. Hammer for help throughout the project. Thank you.